Thanks, Ellis. Yeah, today I'll tell you about some progress that we've made on the question of solving linear programs in strongly polynomial time. So I'm sure most of, or if not all of you, know what LPs is, but I'll start by placing emphasis on the difference between what a polynomial algorithm is and what a strongly polynomial algorithm is. And then we'll move on to look at this subclass of LPs, namely the ones with have at most 2 variables per inequality, and show how it is actually equivalent to a well-structured problem on graphs. And then finally, we will present a strongly polynomial algorithm for it, which is an interior point method. So this is LP. Linear programs is the problem of minimizing or maximizing a linear function subject to linear inequalities. Here on the primal side, we have what is called standard equality form. And its dual is the standard inequality form, which probably most of you are more familiar with. So these are the founding fathers of the field. And as you can tell from the years, they're sort of this field was sort of invented during World War II, motivated by problems in military operations and logistics, but has since found more applications in commerce and other areas today. So an input to a linear program is the constraint matrix A, the right-hand side vector B, and the cost vector C. We'll use L to denote the total bit length of the input, which is the total number of bits you need to encode the numbers in A, B, and C. So a polynomial algorithm is any algorithm that runs in poly MNL time. There are 2 well-known classes of polynomial algorithms for linear programming. The first is what's called the ellipsoid method, given by Kachian. And the second class are called interior point methods, first developed by Karmarkar and Renegar, which will be the focus of today's talk. In practice, actually, most linear programs are solved using the simplex method, which is a method that starts from an initial feasible vertex, and it moves along edges of the polyhedron until you arrive at an optimal vertex. Currently, we do not know whether this method has a polynomial pivot rule that ensures that it terminates in polynomial time. However, it is used in practice widely because it is efficient empirically. So what is strongly polynomial? It is essentially a strengthening of the notion of polynomial time. So we say that an algorithm is strongly polynomial if it uses poly-MN elementary arithmetic operations. So these are your usual plus, minus, multiply, divide, and comparison between 2 numbers. And note that the number of such elementary operations can only depend on the dimension of your problem. So L is no longer part of the running time. And the second requirement is sort of the technical one, which says that the algorithm should run in poly-MNL space. So here L shows up, and this is reasonable because you need that much space in order to store the input anyways. But the crucial difference to polynomial time is that the number of operations that you perform should not depend on the bit encoding length. So no matter how large the numbers are, the number of operations you perform should stay roughly the same. Okay. So one of the outstanding open problems in the theory of optimization is whether there exists a strongly polynomial algorithm for linear programming. This was first posed by Megiddo back in the 80s and is now popularized by Stephen Smale, an applied mathematician who compiled a list of around 20 problems for math this century. And it's the 9th problem on the list. So here's a bird's eye view of the different subclasses of LPs that we know. So from a strongly polynomial point of view. So for a lot of our favorite graph problems like shortest path, bipartite matching, max flow, min cost flow, we have not only polynomial algorithms, but strongly polynomial algorithms for these combinatorial optimization problems. So the study of strongly polynomial originated in combinatorial optimization. And essentially, Smale's question is asking, what other classes of LPs can we solve in strongly polynomial time, if not all? So for these graph problems, we all know that they can be formulated as a linear program. And by a seminal result of Tardosh, she defined a superclass of such LPs called combinatorial LPs and gave a strongly polynomial algorithm for this class. There are some other instances of LPs outside of this class that we also know how to solve in strongly polynomial time, such as the feasibility problem of linear programs with at most 2 variables per inequality. The maximum generalized flow problem is essentially the dual of this problem. So you take the dual of such an LP, you get an LP with at most 2 non-zeros per column. And the maximum generalized flow is essentially the feasibility problem for such LPs. There's also this class called discounted MDP. MDP stands for Markov decision process. They can be formulated as an LP, and we also have strongly polynomial algorithms for them. So this is roughly the state of the art of strongly polynomial computability before 2024. I should remark that any LP can be strongly polynomially reduced to one with at most 3 variables per inequality. I think it's okay. Yeah. Thanks. Yeah. So like if you restrict to at most 3 variables per inequality, this essentially captures all LPs. And so the main result of today's talk is to solve the optimization variant of these 2 problems. So these are both feasibility problems. And so we move the optimization variant into the strongly polynomial frontier. Okay. Good. So now let's focus on this subclass of LPs with at most 2 variables per inequality. By a well-known reduction of Hochbaum, we know that any 2 variable per inequality LP can be reduced to the following monotone form. So what do I mean by monotone? Is that not only does every inequality have at most 2 variables per inequality, it has exactly 1 with positive coefficient and 1 with negative coefficient. And by rescaling, you can assume that the negative coefficient is -1. So every inequality is of this form. This is what we call monotone, 2 variable per inequality LP. Now, because it's 2 variable, you can think of this as corresponding to a graph. So each constraint will represent an arc in a directed multigraph. And the variables yi, yj will correspond to nodes of this graph. So, so we'll denote G as the graph representation of such a monotone 2VPI LP. And throughout this talk, N will represent the number of nodes and M the number of edges. And we'll call this positive gamma E factor for every arc, the gain factor of that arc. Okay. Now, this might still seem a bit like nebulous as to what we're trying to solve for this LP. So we're going to take the dual. If we take the dual of that LP, we get the following linear program. Now it's in standard equality form. And this problem actually has a very nice interpretation. If you sort of ignore the gamma E factors for every arc, then this is just a minimum cost flow problem on graphs, right? You have a constraint for every node. The inflow minus the outflow should equal a prescribed node demand, BV. Now, having these gain factors sort of generalize the problem a bit more by saying that, oh, if I send some flow on an arc, then the flow is scaled by the corresponding gain factor. So let's say if this arc has gain factor 1/2, and you put 20 units of flow on it, only 10 units of flow leave the arc. So this generality allows you to like model a variety of problems, such as, let's say, if you have a pipe network that has leakages, or energy transmission network that has energy loss, or even in a financial setting where you're doing currency exchange. So each node would be a currency, and the gain factor on the arc would represent the exchange rate of those two currencies. So yeah, and then the problem is just the same. We want that the sum of inflows, where the inflow is scaled by the gain factor, minus the outflow equals to the node demand BV for every node. So we call this problem the minimum cost generalized flow problem. And we want to find such a feasible flow with the smallest possible cost. Is the problem clear? So this is kind of what we know about the algorithms for the generalized flow problem before our work. As I've mentioned before, we already have polynomial and strongly polynomial algorithms for the primal feasibility and the dual feasibility problem, but we still don't have a strongly polynomial algorithm for the optimization problem. And the only known algorithm for optimization is an algorithm by Wayne back in 2000s. So the main theorem is that we give a strongly polynomial algorithm for the min cost generalized flow problem, and thanks to the reduction by Hochbaum, this implies that we also have a strongly polynomial algorithm with at most 2 variables per inequality. Yes?
What is this algorithm of Wayne? Like, why doesn't that result just follow from linear programming? Like polynomial? Okay.
It does follow from linear programming. Wayne gave a more specialized algorithm for the generalized flow that has a better running time. Yeah. Okay. And this the algorithm surprisingly is an interior point method, which sort of represents a departure from previous strongly polynomial algorithm approaches. Previously, they were all like sort of combinatorial algorithms in that they're graph-based. But here, we're relying on a continuous optimization method to get a strongly polynomial running time. So to sort of discuss this result, I'll need to provide some prerequisites, namely what an interior point method is. And I'll also introduce a new notion of complexity for linear program called the straight line complexity. Okay, so to talk about interior point methods, it's important to discuss what the central path is. So recall linear programs in standard equality form, right? Minimize C transpose X such that AX equals to BX non-negative. We will now add like an extra penalty term in the objective, which is like minus mu of sum of logs, 1 for every variable. And this is called the log barrier term. Now, if you sort of optimize this augmented problem instead, you'll get some solution. And the solution will be unique because the objective is strictly convex because of log. And moreover, because log of 0 is minus infinity, this sort of encourages the solution to stay far away from 0 on every coordinate. So for every parameter value mu, we get like an optimal solution xcp of mu to this augmented problem. If we collect all these optimal solutions for every value of mu, this traces out a curve in your feasible region called the central path. And this curve will be smooth, and it starts from somewhere deep in your polyhedron, and then it slowly like snakes its way towards an optimal solution. So imagine mu is a parameter that you can toggle. When mu is very large, the objective function essentially plays no role. So you're optimizing to be as far away from 0 on every coordinate. So you're deep inside the polyhedron. Now, as you decrease the value of mu, the influence on the log barrier term reduces, and the solution now will slowly make its way towards the true optimal solution of your original linear program. So as mu converges to 0, the central path converges to an optimal solution of your linear program.
What do you mean the curve is most?
It's like differentiable. Yeah, the derivative is well defined at every point. Yeah. So what do interior point methods do on a very high level is that you start somewhere close to the central path, and then you slowly walk down the central path with geometrically decreasing mu. So you can think of the central path as a highway that takes you to the optimal solution. So for this talk, it will be useful to reparameterize the central path. So remember, previously the central path was parameterized in terms of this penalty value mu. I'm going to reparameterize it by the optimality gap instead. So what's the optimality gap? It's the difference between your current value and the optimal value. So geometrically, you can think of it as I pick some gap value g. I look at the hyperplane given by all solutions that have that gap value. And then the central path will intersect this hyperplane precisely at one point. So this is a valid reparameterization of the central path in terms of the optimality gap. Okay. So as I've said, the intuition of the central path is that every coordinate is approximately as big as possible, so as far away from 0 as possible, subject to gap bound g. Right? So xcp of g is some point in the polyhedron intersected with like this line that stays away from every inequality as far as possible. So it turns out that the central path point at g is almost as far away from the maximum distance that you can get from every inequality. So it's like a 1 over n factor away. So this sort of motivates the definition of what we call max central path. So this is essentially the furthest away you can get from 0 on each coordinate, right? So I'm maximizing the ith coordinate subject to being feasible to my polyhedron and has optimality gap at most g. So in this picture, you can imagine I'm taking the intersection of this polyhedron with this half space, and then I'm looking at, oh, what is the furthest away I can get from every constraint? Like, if this is the constraint that I'm looking at, then the furthest away that I can get from that constraint is this point, right? I do this for every constraint, then I get this ximcp value. Is that clear? So this max central path tells you how far away you can get from every constraint, subject to gap bound g. Now, it turns out that the max central path characterizes the central path very well. So the central path is pointwise at most the max central path. This is by definition, because the max central path is the maximum distance you can get away, and the central path is some feasible solution that has gap at most g. On the other hand, the central path is also lower bounded by a scaled down version of the max central path. In particular, scaled down by 1 over 2m. So this theorem sort of tells you that if you want to understand the central path, it suffices to study the max central path. Yes?
Yeah, sorry.
I'm just reading this definition here that it seems that each coordinate of this is defined separately.
Yes, that's right.
Be a different x for each.
That's right. That's a good point. Yes. The argmax of this program could be different for every I. But we're only concatenating the optimal value. So the resulting vector that you get may not be feasible to your polyhedron.
Okay, yeah, that's my question.
Yeah. Yes.
X is a vector, right?
X is a vector, yeah.
Is XCP a vector?
XCP is also a vector, yes.
So how am I reading that inequality chain at the bottom? It's a bunch of vectors that are bigger than other vectors?
This one?
Yeah.
Yeah, this is coordinate-wise. Coordinate-wise.
Okay.
Yeah. Mm-hmm. So it's saying like on every coordinate, the central path is sandwiched between the max central path and the scaled down version of the max central path. So this sort of tells you that the central path is sufficiently far away from every inequality. Yeah. For like a fixed G, yeah. Yeah. Mm-hmm. Or if you think of like G as varying, then this is like a sandwiching for functions. Yeah. Any other questions? Yeah.
So when we're reparameterizing the path, is it expected that we already know the optimal solution X star? Otherwise, how do we do that?
Sorry, can you repeat your question?
So when we're reparameterizing the path using the optimal solution, is
Yes.
the expectation that we already know the optimal solution?
We're not computing things, so it's fine. Yeah. It's just for the analysis. Good question. Okay. Good. So the takeaway is central path is deep in the polyhedron, and how deep it is measured by this proxy, max central path, which represents the maximum that you can get away from any coordinate. Okay, so why do we even define this max central path? Because it has some really nice properties. So let's fix a coordinate I and look at the max central path on that coordinate. In general, it's going to be a piecewise linear, non-decreasing concave function. And by the previous theorem, we know that if we pick theta to be 1 over 2m or smaller, then the central path will lie in this gray region, the theta neighborhood of the max central path. But you know, like the central path could do some weird things, like it could go up and down, it might not be monotone, there's no concavity. So we instead prefer to study the central path from the lens of the max central path. So interior point methods, they follow the central path towards an optimal solution, which means they stay close to the central path. So if you pick theta to be like smaller than 1 over 2m, you can essentially trap the trajectory of the algorithm in the theta neighborhood as well. So this could be a potential trajectory of the interior point method. In every iteration of the interior point method, what it does is it starts from some point close to the central path. It computes a direction to move by solving a Newton system. And then it moves in that direction until it realizes it goes too far away from the central path, and then it stops. And then it repeats the procedure again. So you can think of the trajectory of the interior point method as a piecewise linear curve that's in the theta neighborhood of the max central path for some small enough theta. Yes?
So why do we not have to also scale up the max central path here? It couldn't be the case that the central path is basically exactly the max central path, and then the interior point method jumps out of the gray region.
Right. So the interior point method always maintains feasibility.
Okay.
So like it cannot exceed the max central path because that's like the maximum distance you can get away from any constraint, maximum slack. So good. So now we're ready to define the crucial notion that underlies our result called straight line complexity. So the straight line complexity of the IF coordinate of the max central path in the theta neighborhood, which we'll denote as like SLC theta of the max central path, is the minimum number of pieces of a piecewise affine function such that it lies in the theta neighborhood, right? So can someone tell me what the minimum number of pieces we need to stay in this example, the theta neighborhood of this example?
2.
Yeah, 2, right? Obviously, you cannot do 1 because this area is very narrow. So this sort of limits like the line segment that you can place. But once you like exit this narrow region, then it's like a straight line to the end. So the straight line complexity for this example is 2, as indicated by the blue curve. Right. So since any interior point method generates a piecewise linear curve in the theta neighborhood of the max central path, the number of iterations required by an interior point method is lower bounded by the straight line complexity of any coordinate. Right? Surprisingly, Alemijon, Dadush, Loho, Natura, and Vey, they design an interior point method which solves an LP in the number of iterations that's essentially parameterized by the sum of the straight line complexity on every coordinate up to a small, strongly polynomial overhead. So you can essentially ignore like this term and just look at this sum. So the lower bound is the max straight line complexity on every coordinate. And the upper bound, the algorithm they give, is parameterized by the sum of the straight line complexities on every coordinate. So it's like ignoring the first term is essentially optimal up to a factor m, which is remarkable, I think. And this is the algorithm that we will use to solve the minimum cost generalized flow problem. Okay, so our main technical contribution is that we show that for the minimum cost generalized flow problem, the straight line complexity of every coordinate is strongly polynomially bounded. So if you have a graph with n nodes and m arcs, then the straight line complexity in the 1 over m neighborhood of the max central path on any edge is order mn log mn. So if you combine this with the previous running time of this theorem, the sum here is going to be a strongly polynomial term, right? It's going to be poly mn, and this is also strongly polynomial. So this shows that their interior point method terminates in a strongly polynomial number of iterations for the minimum cost generalized flow problem. Yeah, so we obtained this. And I won't go too much into detail about the algorithm. I will, in the remaining part of my talk, I'll try to sort of highlight the proof strategy that we use for this SLC theorem up here. And the key ingredient that we will use to bound the straight line complexity is circuits. Yes?
Are there like super strongly polynomial lower bounds for the straight line complexity of general LPs?
That's a very good question. I was planning to only get to that at my last slide. Okay. Yeah, maybe I won't spoil it and get to it. Yeah.
I'll be waiting inside.
Okay. Any other questions? Good. So what are circuits? Okay, here's the formal definition. Let's look at the subspace given by the kernel of A, the constraint matrix. A circuit is any non-zero vector in your subspace that is support minimal, meaning that you cannot find another non-zero vector in your subspace whose support is a strict subset of your vector. So circuits are support minimal vectors of your subspace that are not zero. So I think it's best to illustrate this with an example. Let's assume that A is the constraint matrix of a regular network flow problem, right? Then AX equals to B essentially says that inflow minus outflow is equal to BV for every node V. So what is our subspace given by the kernel of A? You just set B to 0, and the kernel of A is the set of circulations of your graph. Now we know that by the circulation decomposition theorem, every circulation can be decomposed into cycles. And since a cycle is clearly support minimal, like you cannot remove an edge while maintaining net flow 0 everywhere, cycles are precisely circuits for network flow. Okay. So here the matrix is like the regular like node arc incidence matrix, and FC is sort of the flow induced on this cycle, which is the same on every edge. And you can scale it up and down. It's not unique, but it's unique up to scaling. Okay. So what about generalized flow? For generalized flow, the constraints are a bit more complicated because we now have this extra gain factor on every arc. So the kernel of A is going to be the set of generalized circulations, solutions to AX equal to 0. Turns out the circuits of generalized flow are very well behaved. There are essentially two types. The first type is what we call a conservative cycle. So this is like a directed cycle where the product of the gain factors on the cycle is equal to 1. So when you push flow around the cycle, you end up with 0 excess from where you started. The second type is more complicated, and it's called a bicycle. It consists of a cycle whose product of gain factors is greater than 1. So it's flow generating. When you push flow around the cycle, you actually end up with slightly more, not slightly more, but more than what you have. And then in order to maintain net flow 0 everywhere, you need to destroy this excess somehow. So you're going to shift it along a path to a flow absorbing cycle, a cycle whose product of gain factors is less than 1. So when you push flow around this flow absorbing cycle, you end up with less than what you had. So by pushing it around it like infinitely many times, you can like destroy this excess completely. So these are essentially the two types of circuits we have. Yeah.
So I guess when you were describing generalized flow at the beginning, you said leaky pipes. I assumed all of the gammas were going to be strictly less than 1.
Yes.
I guess it's not necessarily the case.
Not necessarily the case.
If they are strictly less than 1, then what do your circuits look like? / can you not have any circuits or something?
That's a good question. So I argue that you will still get these two types. Right? Now you're asking why, if the gain factors are less than 1, do I get a cycle that's flow generating? It's because we look at the residual graph. And so like if you like send flow backwards, anything that's like gamma, the backward arc will have gain factor 1 over gamma. So you will still have a flow generating cycle, even if you started with the assumption that every gain factor is less than 1. Yeah. Okay. So we're going to heavily exploit the structure of generalized flow circuits to upper bound the straight line complexity. But before I go into that, I'll just give you sort of like a general recipe for upper bounding the straight line complexity of your favorite LP. So let's take a vector f in the kernel of A, and let's assume it has positive cost. It naturally induces a line segment. What is this line segment? You start from an optimal solution of your LP, x star, and then you move along this kernel direction until you hit the boundary of your polyhedron, right? So because it's in the kernel direction, AX equals to B is maintained, but you might be lowering some coordinates to 0. So like you go as far as you can until some coordinate hits 0. So this is the line segment that I'm talking about. Every kernel vector induces this line segment once you fix an optimal solution to travel from. And I'm going to parameterize this line segment by G, which is the optimality gap. It just tells me how far I can go along this direction without violating my cost bound, right? So if I have a cost budget of G, the maximum number of units that I can take F is like G divided by the cost of F, right? So this is a line segment. So let's just focus on a single coordinate and see how it looks like. Assuming that like F is positive on coordinate E, the coordinate of our interest. So as you increase the cost budget, you can like take positive multiples of F. So you get this like linear piece that's increasing until some coordinate hits 0. And then you can no longer travel anymore along this direction. So it stays flat even though you continue to increase your cost budget G. So I'm going to use this representation. I'm going to refer to this blue curve as a simple curve that corresponds to my kernel vector F. Is that clear? The slope of this curve sort of measures how expensive your vector is. Right? The more expensive it is, the smaller the gradient is, because you're not like gaining much on coordinate E with like a fixed cost budget. The cheaper it is, the steeper it becomes. Okay. So here's a nice fact that we will use, which is that if you consider the simple curve for every circuit of your subspace, and then you take their pointwise maximum, it's going to lie in the 1/m neighborhood of the max central path. So what do I mean by this? Let's say these are all my circuits, and they're corresponding simple curves, and I take their pointwise maximum. Okay. Then this pointwise maximum curve, which is indicated by dark blue here, lies in the 1/m neighborhood of my max central path. So in light of this fact, our strategy now is to find a set of kernel vectors whose pointwise maximum curve dominates this blue curve. Right? There could be like exponentially many circuits, and the resulting pointwise maximum curve might have many, many pieces, but we just want a curve that has like polynomial number of pieces. So instead of like using like the circuit pointwise maximum curve, we will find a small set of kernel vectors that dominates this blue curve and has small cardinality. So like, let's say I take these two red curves correspond to the vectors in S, my representative set. If I take like the pointwise maximum curve, it lies above the blue curve. So this is what I mean by dominate. And notice that it only has 4 linear pieces, right? In general, if your set S has like L vectors, then the pointwise maximum curve will have at most 2 L pieces. So as long as you can like pick a small set S, you win, because you have successfully exhibited a piecewise affine curve with small number of pieces in the 1/m neighborhood of the max central path. That's essentially straight line complexity. Yes?
Can you translate this into something like graphy with circuits? So it's like...
Yeah. Next slide I will do it. Yeah, next slide I will do it. Any questions? Yeah, I know everything is a bit like heavy with all the notations, so feel free to ask. Yes?
Didn't you have 2m at some point, and now it's m? I guess it doesn't matter.
2m for... Oh, I see, the neighborhood size, you mean? Yeah, so it turns out that the neighborhood size is not crucial. Like if you have a curve in some neighborhood, you can always like find another curve in like a different neighborhood, and then you pay like a small factor. So like as long as you show it for one neighborhood, you're done. Right. This I'm sweeping a lot of details under the rug.
Okay, so now I'm using I guess I'm jointing cycles. They are no longer simple cycles anymore, but I can
Yes.
show that it dominates this dark blue curve.
Yes.
And also stays within this.
Yes, exactly.
That's why it's SLC.
Exactly. Yeah. So when you say joining cycles, you mean in the graph world, that's what we're doing, right?
Right.
Yeah, because we're no longer looking at support minimal circulations. We're looking at circulations. Yeah.
Which you're going to tell us about.
Yes, that's right. That's right. Good. Any other questions? Is the strategy clear? Okay. Sorry. Yeah. So our goal now is to find a small set of kernel vectors or circulations in our case that dominates this like blue curve given by the set of all circuits. Okay. So that's our goal. Our goal is to dominate circuits. Now recall, for generalized flow, we have nice circuits. They are conservative cycles or bicycles. So let's just look at the bicycle because it's more interesting. And let's fix an edge in the bicycle. Let's say it's this middle edge here. These blue numbers are just the flow that's induced by the bicycle. And I've drawn here the simple curve associated with this bicycle on arc E. So what does it mean for a kernel vector to dominate this circuit? So let's say I give you a kernel vector f, and the red curve is its simple curve on E. So both of them contain E. So it means that it lies above the curve, obviously. But what does that even mean? So let's first look at this like constant piece. It means that you can send more flow on E, on F, via F, than via the circuit. Now for this increasing piece, remember I said that the steeper the gradient, the cheaper the cost is. So the red curve is steeper, so it means that it's cheaper to send flow on E via F than via the circuit C. So that's what it means to dominate. It means for vector F to dominate a circuit C. It's like two criterias: the cost of sending the flow and what's the maximum amount of flow you can send. Okay. Yeah.
So if I forget about generalized flow for a second, this is then if it's regular flow.
Yeah.
You're just saying find me a cheaper cycle whose smallest the amount of remaining capacity on its edges is larger.
Yes.
Than the cycle I'm trying to dominate.
Yes. Mm-hmm. So that's like the maximum part, and then cheaper is the increasing part. Yeah. Mm-hmm. But with gain factors, you know, even though you might have a large capacity, it doesn't mean that it's going to dominate, because it depends on how much the flow gets scaled when it reaches that maximum capacity arc. Yeah. Okay, so we're going to dominate circuits now. But circuits are kind of painful to work with because it has many parts. So we're going to sort of decompose it into paths instead. Right? So for a bicycle, for example, there's like 2 cycles and a path. And you can really think of a cycle as like a path that comes back onto itself. So we're going to dominate paths instead. Again, I'm sweeping details under the rug. I'm just reducing it to this problem. So suppose I give you an ST walk. I'm going to use FW to be the unit flow on the walk. So by unit flow, I mean that the walk ships 1 unit of flow to T. Okay? So you can sort of like deduce the flow on every arc, like starting from T, right? We know that we need to ship like 1 unit of flow to T. So on the last arc, this equality should be true. And then like you can work your way backwards, like on all the intermediate nodes, net flow of 0 should be preserved. Of course, I'm cheating a little bit here because you could like reuse arcs. So this is not really like the actual formula. But between friends, let's assume this walk doesn't reuse arcs. Okay? Then the unit flow is just given by this formula. Okay, so here's the setting. we have non-negative arc cost and positive arc capacities on every arc. Given two ST walks W and W prime, I say that W prime dominates W if the following conditions hold. The first is that, this circle is the Hadamard product. So inside is a vector. I'm taking the infinity norm. So this is like the cost of flow on W prime, and this is the cost of flow on W. The true cost would be L1 norm because you would sum up all the contributions. But here I'm taking the infinity norm as like a good proxy. They're going to be off by a factor n, but yeah, who cares? So W prime dominates W if its infinity norm cost is cheaper than W. That's criteria number one. Criteria number two is I can send more flow to T on W prime compared to W. So what's the maximum amount of flow I can send? It's this ratio, right? This is again like Hadamard ratio. Like you take the coordinate like wise ratio of the corresponding entries of the two vectors. So this tells you like what's the arc with like the maximum usage, right? And that will be the bottleneck arc that determines the maximum amount of flow you can send on that walk. So this says that W prime can send more flow to T than W. And the last condition is that W prime is more efficient, meaning that if you take the product of all the gain factors on W prime, it's larger than W. This essentially means that you only need less flow from S in order to end up with 1 unit of flow at T in W prime compared to W. Right?
Why is the third condition?
It's like a technical condition that we will use. But for the purposes of this talk, you don't have to understand why we need this. Because so far I've only discussed about cost and maximum amount of flow you can send. This is sort of like an additional thing that we impose, but it's going to be useful for our proofs in the paper. So these are the three criteria for domination when comparing two ST walks. So now the core problem is to find a small set of ST walks such that every ST path is dominated by some walk in W. This is our final goal. I've reduced domination all the way from like first bound SLC to dominating circuits, then dominating circuits to dominating paths. This is the final boss. Yeah.
Wait, did you say what the reduction is from circuits?
No, I did not. Yeah. I did not. Yeah. But this is the essential core problem that we need to solve. Okay. So we show that for every pair of vertices, there exists a set of m square walks that dominates every ST path in the graph. Note that there could be exponentially many ST paths in the graph. So how do we prove this? We're going to like assign a combinatorial signature to a walk. So these signatures kind of make sense because they're essentially the argmax of like the infinity norm here, right? So EC is the cost bottleneck. It tells me what's the most expensive arc in my walk. And EF is the flow bottleneck, which tells me which arc constrains the maximum flow I can send on W. Okay? So here's an example. The costs are all 1, and these are the upper bounds. Can you guys tell me what EC is? What's the cost bottleneck? Yeah, exactly. Because you take the inner product of C and FW, whichever one is the biggest, is like EC. And what's EF? The flow bottleneck. So, yeah, 2. You scale this FW flow up until you hit some upper bound. So the maximum scaling factor is 2, and it's like constricted by this arc. So that's the flow bottleneck. Is that clear? The rest, like, you can scale more. This you can scale by 8, this can scale by 7/3, and this is by 10/4. So that's the most constraining one. Okay. So, okay, now let's suppose we have some ST path with some signature, ECEF. I'm going to define this operation called patching. So what it does is it looks at the ECEF subpath and it replaces it by a max gain ECEF subpath of the same signature. So I replace the ECEF subpath by a max gain ECEF subpath that preserves the signature. Right? This is a well-defined operation. There are only like finitely many paths. So I can always like patch this subpath with a max gain ECEF subpath. So what are some properties that you can gain from doing this patching operation? The first is that patch P, which is the path that you get after patching, dominates the original path that you started with. So on those 3 measures that I talked about. Yeah.
Sorry, what was gain? Was the product of the...
Yes, sorry. Yeah, the product of the gain factors along the subpath. So, and there's a nice thing that happens when you do this patching operation. The signature changes in a very predictable way. Either the signature remains the same, or the first signature will move forward. So the second signature will not change, but the first signature either remains the same or it's going to jump forward to this section of the path. So either it's this or it jumps forward. Okay? So now I can iterate this operation. I start with some ST path, and I'm going to like iteratively patch it until the signature stops changing. So the signature stabilizes, and then I end up with some WK, some ST walk. By the patching lemma, I know that my final walk dominates the initial starting path. Moreover, I know that I only need to perform at most n patches, right? Because this part of this, we started with an ST path. This is a subpath. So each time it jumps forward, so you run out of edges eventually. So you only need to patch at most n times. So how does this WK look like, right? We know that it is obtained by replacing ECEF with some max gain ECEF subpath. On the left, we have some walk that starts from S and ends at EC. And we know that it's n recurrent, meaning that it uses like every arc at most n times. And this is because we patched at most n times. On the right, we know that it's going to remain a path, EFT path. Is that clear? So we know that when we start from an ST path and perform this patching operation, we're going to end up with such a structure. ST walk given by such a structure. So this sort of like motivates our construction of the dominating set of walks. Essentially, for every signature, we're going to construct like a walk that looks like this. So we start from, we fix the signature ECEF. The middle part is going to be a max gain ECEF path with the same signature. On the left, we're going to append a max gain n recurrent walk that starts from S and terminates at EC that preserves the signature of the whole thing. And then on the right, we're going to append a max gain EFT path, which also preserves the signature of the whole thing. Okay? So for every signature, we have such a walk. Yeah, and if ECEF has like opposite positions, then you can do the same thing. Since there are only m square signatures, this gives us m square walks. So that's the construction. So this is my last slide. Hopefully I've satisfied the curiosity of people who are interested in the proof. So we've shown that the straight line complexity of minimum cost generalized flow is strongly polynomially bounded. This implies a strongly polynomial algorithm for LPs with at most 2 variables per inequality. Now, back to Alice's question, whether there is a subclass of LPs with super strongly polynomial straight line complexity. The answer is yes, unfortunately. So Alamijian, Benkimo, Gobet, and Josevic constructed a family of LPs that has exponential. So not only super polynomial, but exponential. So this sort of says that, like, if you want to solve Smale's 9 problem, don't use SLC. It's not going to work. So yeah, I'll conclude with some future directions. So like an obvious one is, what other subclasses of LPs have strongly polynomial straight line complexity? We've shown that this is true for LPs with at most 2 non-zeros per row or per column. So now you have to move to 3. So in that class, can you identify like a meaningful subclass that has strongly polynomial SLC? And yeah, the other direction is to give a faster strongly polynomial algorithm for the generalized flow problem. The current one relies on the interior point method of Alamijian et al., which is quite slow. So I think it would be interesting to come up with like something that's fast, strongly polynomial, and maybe combinatorial, meaning like, you know, you don't rely on continuous optimization methods. Yeah, and that's all that I have to say. Thank you very much.
Are there any questions for Cedric? You might how you can go from abstract loss to MN log.
Oh yeah, yeah. So that requires a more like careful argument. It doesn't use path patching. It uses a more involved patching process that just patches like part of the circuit directly instead of decomposing into paths first and then doing the path argument. Yeah.
As you mentioned, there are other strongly polynomial algorithms that are more like combinatorial. Are there like interpretations of them into this straight line complexity?
I see. So you're asking for examples of strongly polynomial algorithms that are combinatorial for well-known combat problems?
Yes. You're trying to like unify the.
Yeah, so those algorithms don't rely on straight line complexity. They show strongly polynomial using like different methods. The straight line complexity is a rather new notion that was introduced only a couple years back. So for example, Dijkstra algorithm is strongly polynomial for shortest path, or Bellman-Ford, let's say, with negative weights. It doesn't rely on straight line complexity, right? It uses a completely different argument. Like max flow, like the pre-flow push algorithm for max flow also relies on a different argument. For min cost flow, there is this like famous result by Tardosh. It uses this like yet another technique for showing strongly polynomial called variable fixing, which essentially means that like once you solve an LP, so you perturb your LP a little bit, your instance a little bit, and then you solve like the resulting instance. And then you can sort of deduce the support of an optimal solution to your original instance by the optimal solution to the perturbed instance. Yet again, another technique. So there are many techniques to show strongly polynomial. Straight line complexity is one of them. Yeah. Thank you.